Okay, the definition of electric field, it is the force felt by a test charge that has a charge of 1 coulomb, a unit charge. A unit means 1 coulomb. A unit charge means 1 coulomb. It is not necessary for the test charge to be there so that the electric field is there. So regardless whether there is a test charge or not. So the term per unit charge means, let's say if we assume that there is a test charge. Let's say if we put a test charge over there, what will be the force? Okay, let's say we have to emphasize on the phrase let's say. It is not necessarily true that the test charge is there, or the test charge could not be there as well. So let's assume that if the test charge is there, then the force felt by 1 coulomb of charge is given by E. So that is the definition. We have a situation here where we play with, the paper rocket, the paper plane. Okay, let's say if I have a fan. For example, I have a big fan here. Okay, big fan. And then it is blowing the wind, right? Towards this direction. So without the paper plane, you should be able to tell that there is the wind speed, right? Whether the plane is there or not there, we know that the wind is there, which is flowing from the fan towards the outer direction. But if we want to quantify the speed of the wind, we have to put the paper plane, or the paper plane could be a detector so that it can detect the speed of the wind. So let's say if you are a kid and then you want to quantify by using your eyes, you want to see whether the wind is blowing fast or slow. So you have your paper plane, and then you put your paper plane in here, in the field. Okay, in the field. I'm not saying the wind as a field. Wind is not actually. It could be a field in terms of geophysics. I'll explain later. So let's say if you put the paper plane here, so you will observe whether the paper plane flies fast or slow. So it depends on the speed of the wind. But if you remove the paper plane, does it mean that the wind speed doesn't exist? It does exist. So same goes to the electric field. Whether we have the test charge or we don't have the test charge, then the electric field is there. So this is the test charge, this is the source charge. You should be able to differentiate between the two. The source charge must always exist so that you have the electric field, okay? But the test charge is hypothetical. Hypothetical means, let's say if we have a test charge, then the test charge will feel this particular force, okay? So the basic equation of electric field. So this is, the electric field is a vector. That's why I'm denoting the electric field using a bold font. So you have the force felt by the hypothetical test charge. Let's say if we have a test charge. So that's the meaning of the test charge. So in the situation here, one of the charges is the source, and then the other is the test charge. So that's why I have Q and Q naught. So because Q naught, I need you to put some annotation there saying that Q naught is the test charge. Okay, Q naught is the test charge. So Q is the charge of the source that creates the electric field, and then R squared is the distance between the source and the test charge. Okay. Let's say if the test charge is far away from the source, then the value of R will be infinitely bigger. Then the value of the force will be 0, and the electric field will be 0 as well. So moving back to the previous lectures, we have discussed in electric field in more details. And then I've also described to you the meaning of electric field, and then what are the properties of the electric field. So I hope you have already revised that while waiting for today's lecture since Monday. So again, I repeat, for the equation 5, it is basically coming from Coulomb's law. But the thing is, you have to remove the charge term for the test charge. So as you can see that, as you can see in equation 5, we only have Q sub I. So that Q sub I is the charge of the corresponding sources of electric field. So here we have we have 3 sources of electric field, this one, and this one. But typically this one is bigger, meaning to say it tries to signify you that the charge is way larger than Q1 and Q2. So you have to add the contributions of the three charges. Okay, you have to add the contribution of the three charges. So meaning to say the index I should be from 1, 2, and 3 because we have three charges. Okay, very intuitive. Let's say if I have a system of 100 charges, so the index should be going from 1 to 100. So you have to identify which charge is I equals to 1 and then which one is I equals to 2. For example, here we have charge number 1 over here and then charge number 2 and charge number 3 over here. So we want, for example, if we want to identify the electric field at this particular point, so supposedly if we assume that if we have a test charge here, what will be the force felt by that particular test charge? So that is the meaning of the electric field. But the force itself must be contributing to 1 coulomb per unit charge. Okay, so the electric field is given by the force felt by a unit charge. When I say a unit charge, it means that the charge, the test charge, I'm not talking about the sources, okay? I'm not talking about the sources, I'm talking about the test charge. If I were, okay, I repeat, yeah, if I were to place my test charge at this particular point, what will be the force felt by that particular test charge? Okay, and then that test charge, the force is equal to the electric field. Okay, the magnitude of the force is equal to the magnitude of the electric field, provided that the test charge is 1 coulomb. Okay, so that's the meaning of the electric field. I hope you are okay. Yeah? So the r cap here means the unit vector specifying the direction of the field. For example, we have Q1, which is pointing towards this direction. So r cap sub 1, okay, r cap sub 1, which is the direction of the electric field, provided by charge number 1 is given by this direction from here to here. Same goes to this one. R cap sub 2 is towards this direction. Are you guys okay? If you are not okay, you can always ask me on WhatsApp now, okay? And then I'll try to have a look at it before I proceed, okay? I'm giving you like 30 seconds. Maybe if you have anything that you cannot understand, so yeah, 1 second. I hope you can see the screen clearly, okay? So because that's the best quality of the screen. So I hope you can see the equation correctly. So we have the E as the bold font, meaning to say E itself is a vector, okay? Okay. When E is not bold, then it is the magnitude. So we are not considering the direction of the electric field. So the reason why we have E as a bold font is because of the R cap inside the equation. So as you can identify here, we have the R cap specifying the direction of each contribution of the electric field contributed by each charge. Okay? So you can always read these together. So now, the equation just now, equation 5, okay, the equation 5 with the summation just now, it's basically applies for the discrete system of charges. Let's say if I have a discrete number of charges, 100 point charges, then I can use equation 5. Okay, equation 5, I can use the equation here. But now, if we have a continuous system, let's say if we are living in a macroscopic world, okay, so that we see a lump of electron as a continuous body, okay? We see the collection of electrons as a whole. So for that situation, we have to use calculus. Because if you could remember that I've explained about calculus before this, calculus is about dividing a big body into a small chunk, into small chunks, into small calculi. So here, if we have an arbitrary shaped body, so we have to consider an infinitesimal amount of charge. And then we assume that small box here, okay? We assume the small box here as a point charge. So we substitute into we substitute into equation 5, okay? We substitute into the form of equation 5. But the thing is, we have to replace the sigma operator here, which is the summation operator, with the integral operator. So now the charge of the small cube here is given by dq. dq is an infinitesimal small charge, okay? An infinitesimal amount of charge contributed by that small box, okay? And then the size of the box, there are 3 boxes, this one, and this one. So let's say if I take one of the boxes, and then I consider that box as dq. The amount of charge contributed by that box is dq, okay? And then I have to consider the distance between the box and the point of interest. For example, if I want to evaluate the electric field strength at this point, okay? I want to know how big is the magnitude of the electric field at this particular point. Then I have to consider the small box here, and then I have to consider the distance between the box and the point here. And then I have to consider another box. And then I have to consider another box, and then another box, and then another box, such that all these boxes, when I union them together, when I put them together, they will form the original body. Do you see what I mean? So I'll show you the one example later. The example that I'm going to show you after this is the electric field due to an infinitely long wire, okay? And then today I'll try to cover the Gauss law, so that you can always find out the electric field by using Coulomb's law and Gauss law as well, okay? So you will discover that Gauss law is way easier than using the formula here, okay? So this is the formula, which is, let's say if you want to evaluate the electric field at a given point, you can use two laws. The first one is by using Coulomb's law, which is the equation here. The equation here is not exactly the Coulomb's law, but the reason why I'm using Coulomb's law because the form of the equation are the same, and then the equation 6 here is derived from Coulomb's law. So again, I need you to remember this, okay? Please remember, because I'm not going to repeat this again. If you want to evaluate the electric field, you have two approaches. The first approach is by using equation 6, okay? Please denote that in your lecture note. You can use equation 6. Normally, we call that as deriving the electric field by using Coulomb's law. And then you can also use Gauss law, which is the alternative approach. If you use Gauss law, then it is way easier, provided that the problem is symmetrical. For example, this problem is not symmetrical. If you look at the shape of the body here, which is an arbitrary shape, so I'm sure that it is not symmetrical, then Gauss law will not be applicable for this kind of body. Let's say if I have a body of charge which is in the form of a sphere, then I can use Gauss law because it is symmetrical. So you have to use your intuition and your experience as a physics student to be able to identify whether the shape is symmetrical or not, okay? So again, I've explained this during the last lecture. We have 3 types of charge densities. We have sigma, we have lambda, we have the rho. So rho is for the volumetric body, 3-dimensional body. And then we have the surface charge density, which accounts for the surface, structure. Let's say if the charge itself is a sheet of paper, then it is considered as the charge density. And then we have the wire, for example, which is the linear charge density, which is given by lambda. So the linear charge density accounts for the 1-dimensional body, okay? Like the wire, like the circle, okay? And then we have a hollow sphere. A hollow sphere, okay? A hollow sphere is considered as a surface, okay? But if the sphere itself is not hollow, then we consider that as the 3-dimensional volume, okay? So I can also transform the equation that I've given here, and here, into the infinitesimal form. Let's say if my charge is very, very small, then I can also use the charge density's definition. I can transform the definition into the differential form. This is the differential form. Let's say I have a large body, a sphere, for that case, I'll use the equation here. Because I know the volume of the sphere given by 4/3 pi r cubed. Let's say if I have a big sphere, okay, and then I know that the desired charge is given by this, then I'll be able to compute the value, or I'll be able to calculate the value of rho. But let's say if I have a sphere which is very, very, very small, which is infinitesimally small, okay, then I can use this form. This is merely a calculus notation, okay? You don't have to worry too much about this. Later, when we derive the electric field using Coulomb's law, then you need to use the three equations here, depending on the problems. Okay, now I want to show you, I want to derive you something. Okay, I want to derive the electric field due to an infinitesimally long wire, the one that I've explained, not really explained, I've introduced to you on Monday, but I did not manage to finish the derivation. So we'll continue here. So suppose that we have, okay, if you don't understand what I'm going to do now, is that my aim now is to show you how to apply equation 6 in your lecture note in order to find out the electric field at a given point. Let's say if I have an infinitely long wire, okay, so I'll use the dotted lines for the two ends. And then let's say if we have the point here, I mean the line here is the x-axis. The line here is the x-axis. So this is the x-axis. So the line here along the wire is given by the y-axis. By the y-axis, okay? And the wire is infinitely long, okay? Very, very long, okay? You imagine that the wire is from Kuala Lumpur to Penang, so that long. And then you yourself, which is this big, which is about your size, and then you will see that the wire is infinitely long. But if you are the giant viewing from the top view of the earth, you know that the wire is actually from Penang to Kuala Lumpur. That is the symbolic example. Okay? So this is the origin, and then we are interested to know the electric field at this particular point. Okay? And then suppose if I select a small length of the wire, then that will be given by dq. If I zoom this, okay, you will see that, let me draw this again, let me draw the wire. You will see that this is my wire, and then I am actually selecting a small length of the wire, a small portion of the wire. So this length from here to here is given by dl. And then the wire has the linear charge density of lambda. So lambda is the linear charge density of the wire. And then this is the zoom in version. Okay, so this is dq. And then I know the position of my dq towards my point E is given by the line here. Okay, so I define the angle phi over here. And then this is 90 degrees here. So I define the distance, from here, I define the distance from here to here as L. So the distance from here to here is given by L. And then the distance, because the position here, the point P here is located exactly on the x-axis. And then the distance from here to here is given by x. So let's say if I take the mirror reflection of the wire, so I'll have another dq over here, from here to here as well. So the distance from here to here is given by r. Same goes to this one, given by r. This is x and this is r. From here to here is r, from here to here is r. So I'm taking the counterpart of this one, the mirror of the point here. So again, the distance from here to here is L. But instead of having L, we have negative L because we have the origin here. So phi is the angle here. From here to here is positive. From here to here is negative. That is the sign convention to enable the correct mathematical derivation. Okay, if you use Coulomb's law, if you use the equation 6, I'm not saying Coulomb's law, which is not legitimate to say that it is the Coulomb's law. I'm going to mention equation 6, okay? If you use equation 6 here, So this is equation 6. So we are going to use the equation here to derive the electric field strength. We want to know how strong is the electric field at this position from the charge wire. Of course, if we go further and further away, then the electric field approaches 0 because the point here, for example here, is far from the wire. But here it is close to the wire, so the value of E should be a number, a value. But as you can see here, the electric field contributed by the bottom DQ, the bottom portion of the wire, is given by this direction. Okay, let me denote this using another color, using the green color. Okay, and then the electric field contributed by the portion of wire here is given by this direction. So you will see that there is the positive Y component and the negative Y component. Because the distance from the element to the position here is the same with the element here to here. They are both the same. So meaning to say the vertical component of the electric field contributed by this guy is exactly the same with the vertical component of the electric field contributed by this guy. So they cancel off. So the Y component of the electric field is 0. I hope that it is intuitive because it is contributed by this direction, by the charge coming from this direction, and it is also contributed by the charge contributed by this direction as well. So the vertical, the component along the y-axis, they are basically cancel off. So this one and this one is cancel off. So we can say that the y component is 0 because they cancel off. Do you have any issues with that? I hope you get the idea, okay? If you got problem with understanding this, then you have to reflect yourself. What have I learned in 101? Okay, next. So we know that the vertical component is 0, and then the electric field will have the horizontal component because we have this direction and this direction, okay? Okay, now let's talk about the electric field along the X component. So we have the electric field element. This guy, this is DE, okay? Because it is an infinitesimal amount of electric charge contributed by an infinitesimal amount of Q. So we have to integrate them together. We have to join them together so that we will be able to know the electric charge due to the entire wire. But now we are talking about one portion, one small portion of the wire. I hope you understand calculus, okay? So the electric field along the differential electric field along the x-axis, or the infinitesimal amount of electric field along the x-axis component, is given by, we have K dq over r squared, and then we have cosine of phi times I, because this is the unit vector along the x-axis, and j is the unit j cap is the unit vector along the vertical axis. But here we are considering the horizontal component, so that's why we have I. So from equation 6, I have replaced my r cap into I cap because I am considering the x-axis direction. But r cap is for the general form. But now I'm considering along the x-axis, then I'm using I cap. Okay. The reason why I'm using cosine of phi is, of course, you have learned this in mechanics 101, because you want the component along the x-axis. Okay. So this angle should be the same with this angle. So DE, so this is DE, cosine of phi is given by the component, the horizontal component here. So this is the blue arrow here is the horizontal component. Okay, next. So you know that your R is given by, this is from here to here is X, from here to here is L. So R is given by L squared plus X squared. You take the square root, right? So I hope you get the idea, because from here to here is X, from here to here is L. So you use Pythagoras theorem to obtain the value of R. You use Pythagoras theorem to obtain the value of R. But here we have R squared. So I have to replace this guy with L squared plus X squared. So dq equals to L squared plus X squared.
because I have the square here, so I have, they cancel off. No, not really cancel off. This square of the square root is the term itself, am I right? So L squared plus X squared. And then cosine of phi. Okay? So I have another, because this is about solving the calculus now. We have already done with the physics. We have developed the equation from the physics. Now we are focusing on the mathematics. So it is based on your skills, based on your based on your experience as a student, where you have used calculus for many years. So you have to use your genius idea, where, okay, you know that the tangent of theta is equals to the opposite divided by the adjacent. So now the opposite is L, because tangent of phi, not theta, I'm sorry. Tangent of phi is given by L over X. Given by L over X. So we have L as X tangent of theta. Okay? So by using the equation here, we want to substitute this guy into this guy. You will have, because this is L squared, so L squared is equals to X squared tangent squared of phi, right? I'm taking the squared. So I'll just substitute this guy into this guy. So I have L squared plus X squared equals to X squared tangent squared of phi plus X squared. So I have this guy over here, right? And then I can just replace this with X squared tangent squared phi plus 1. And then you have to remember, you don't really have to remember, because I'm not going to ask you this kind of question. The reason why I'm giving you the trouble here is because I want you to go through the hassle and the trouble so that you will understand why we are using Gauss law instead of equation 6 to derive the electric field. So you will appreciate Gauss law more after this. So let me show you the hassle. So the trigonometric form here is basically the second of phi. Second squared of phi. Okay? And then I substitute into here. Instead of using this one, I'm just going to delete this, remove this, and then I replace with X squared second squared of phi. Okay? But now let's talk about dq. How do we replace our dq? Because our dq here is not helpful. Because we know that the q here depends on the position. Let's say if I change the position here, then I'll have another r, right? If I use the position here, then I have a different r. So dq here should be dependent on the position. So I'm going to use the charge density equation that I've presented to you just now. So we have L times dl, lambda dl is equals to dq. I'm using the equation here. Using this one. And then we have the infinitesimal version of the charge density here. I'm using this one, okay? So I'm replacing this here to here. But from the equation here, I need you to keep this first, okay? I need you to keep this first. So we want to avoid dl. So we have the tangent of phi equals x tangent of phi equals to L. Am I right? So we have L x tangent of theta. This is not dx, okay? We have x d phi. Because x is a constant, so the value of x here stays the same throughout the situation here. So L equals to x tangent of theta, right? So tangent of phi, not theta, phi, tangent of phi is given by L over x. So that's the reason why I have this one. So I want to change this into the differential form. So I have L as a function of phi. Just now I've mentioned to you that L as a function of x, so my mistake. So L now is a function of phi. So you transform the equation here into the differential form, you will have this, okay? You will need to go back to your calculus, okay? You need to go back to your calculus. So from here, you need to know how to transform this one into this one. So meaning to say your L now is a function of phi. So you have to find, so L as a function of phi. So this is basically a function, yeah? If you differentiate L with respect to phi, you will have x second squared of phi, right? From the equation here, you have dl over d phi is given by x second squared of phi. This is it. If you evaluate this, if you refer to the formula, the calculus formulae, okay, a book of formulae, so you will find that you have this one, and then you bring this guy over here so that you will have this, okay? So I just want to show you that using equation 6 is a hell of a problem. So it is not easy for you to use equation 6, okay? And then you will appreciate Gauss' law more. So you substitute this one into here, okay? Then you will have this one, but instead of dx, you have d phi. Okay, you have d phi. And then you substitute dq, you replace dq here with this one. You will have k lambda second squared of phi, d phi. And then you have to divide by, here you have x squared, right? You have x squared. And then here you also have x over here, if I'm not mistaken, because you have x over here, you substitute in here, you have lambda x here. So they will cancel off this one. You will have only the x at the denominator. And then you also have second squared here. Okay? And then you have the cosine of phi over here, cosine of phi. So this guy and this guy cancel off. What remains is, okay, because we have this, the differential element of the electric field along the x-axis is given by k lambda over x d phi, cosine. So I forgot to put the cosine. So we have the cosine here, cosine of phi d phi. And then the final electric field is given by the integral of k lambda over x cosine of phi d phi. But what are the limits? Okay, because it is infinitely long, meaning to say, let's say, okay, let's say if you look at my hand, the height is from here to here, right? But if it is infinitesimally long, then I have to elevate my hand, which is approximately 90 degrees at my armpit here, 90 degrees. So you have to, because it is very, very long, so the phi here will range from minus pi over 2 to pi over 2. So you will discover that the integral here will not affect the constant here because x stays the same all the time. Am I right? It stays the same all the time. So finally, your integral will only be applied to the cosine of phi. So because the limit is from negative phi over 2 to phi over 2, then it is equals to 1. So what remains is the pure constant over here. So if you replace k with, because k is equal to 1 over 4 pi epsilon naught. If I'm not mistaken, there is, the integral is not equals to 1. Sorry, it should be 2 if I'm not mistaken. Can you help me, my assistant? Can you help me to evaluate the cosine of phi from minus pi over 2 until pi over 2? Just check to see if whether it's equals to 1 or 2. To be honest, I don't remember. But it is, you can always calculate that using the calculator. The integral of cosine from negative pi over 2 to pi over 2 is equals to 2. So basically the final equation here, the final term here, we have k lambda over x times 2. So if you replace this one, k, with this one, so you will have k lambda, sorry, not k, lambda over, because we have 4 here and then we have 2 over here, then we have 2 pi epsilon naught, oh no, epsilon naught, and then we have x, where x is the distance from the point here to the wire along the x-axis. So it's not easy for you to evaluate this, so you have to focus on the calculus. So yeah, that's the idea. So later, after this, I'm going to teach you Gauss' law, and then you can derive this easily without doing this crazy mathematics, okay? So of course, I've explained to you about the electric field lines. So if after this, when you see the arrows, so you don't, you have to know that these arrows are the electric field lines, and then they are not physically exist. they are merely, a representation of electric field that allow us to understand this easily, okay? So I need you to inspect the electric field lines. Okay, for example, at this particular point, the magnitude of the electric field from at this point, you see the arrow, my arrow here, is larger than the electric field over here. Do you know the reason why? The reason is because the point here is closer to the source. Okay? It is stronger here compared to this position. The closer the position to the source, then the stronger the electric field strength. Okay? And then we have the equal electric field contour. So meaning to say, if I draw this again, so this is my positive, so this is my line. So the point here will have a larger magnitude compared to this point, A and B. The electric field at point A, the magnitude is larger than B. Let's say if I draw this radially upwards, okay? So the contour here, the contour here, the distance from the contour towards the source should be the same because it is the circle. So this is the center point, this is the radius, right? So the radius will always be the same. So meaning to say the electric field strength for this particular configuration, which is a point source, okay? Which applies to this particular situation only. The electric fields on the contour lines have the same magnitude. So that's the idea. So here we'll have a smaller magnitude, but the magnitude here, as long as it is on the same contour line, then they are exactly the same. So you have to understand this. If you don't understand this now, then you will have problem in understanding Gauss law later on. Because I'm going to ask you a lot of Gauss law questions in the examination. Okay? Yeah, I hope you get the idea. So this is about the electric field lines. Just now, I've mentioned to you that on the same electric field lines, but if we have two different positions, okay, then the magnitude will be different. But here we have another concept, which is the electric field flux. I'm going to introduce you to the flux after this. But as you can see here, the flux, the number of electric field lines that go through surface A and surface B, they are the same. Okay? The number of lines are the same, 1, 2, 3, 4, 5, 6, and the same goes to this one, 1, 2, 3, 4, 5, 6. So meaning to say the flux will be the same. The flux here and the flux here, Flux. I'll introduce after this. But the strength, the magnitude of the electric fields will be different because, for example, if I have my source over here, then surface A is closer to my source. Then the magnitude of the electric field felt by surface A will be greater than surface B. That's the idea. If you cannot catch this, I'll record myself and then you watch my video, okay? For this one, the electric field here is 0. And then, of course, the electric field strength here is greater than the electric field strength at B. Because I am assuming that both charges are identical. They have the same magnitude of charge. So I'm assuming if I remove the other half, then it will radially pointing outwards. I mean, the electric field lines will radially pointing outwards of the charge. But now we have two like charges, then they will repel each other. Then the electric field lines will look like this. This is intuitive, okay? So it means to say at this point, the electric field strength, the net electric field, yeah? The net is equal to 0. Is equal to a 0 vector, okay? And then we have the dipole. So this is the situation where you can always predict this because it will point out from the positive charge towards the negative charge. So you can always read this. So let's say if this charge is larger than the charge here, and then they are opposite in signs, then you have this particular form. But of course, you can have even more complicated situations.